Okay. I propose to start. So first of all, so welcome to this second session of the webinar. Maybe if you have some question, I can answer to all your questions about the first part. In other case, I propose to start with the second part. Do you see my screen? Yes. It's okay, you see? Okay, my screen. Just let me restart. Great. Okay, so yesterday we have learned many general things about machine learning in general, so the basic definitions and the general principles of the implementation of a machine learning algorithm. And today we now start by detailing some specific algorithm. And one of the most basic machine learning algorithm for classification and regression is a regression tree. So regression tree or classification tree, also the decision tree in general, are not often used, but they constitute the basis of some more complex algorithms, which are named ensemble methods. Okay, and this is why I propose to teach in detail what we call decision tree, and to well understand the structure of a decision tree, to well understand the general idea and the implementation of a decision tree, to well understand the extension that we call the ensemble methods. Okay. So let me start with the objective of this section. So the first is to understand the concept of decision tree. Then for a decision tree, there are many algorithms to produce a decision tree. And we will detail the most famous algorithm, which is a CART algorithm proposed by Breman. In this algorithm, the baseline principle is the principle of the binary division. Okay, and we'll understand what is a binary division. So we will introduce some definitions of what we call a root, a node, a leaf. We will also define what we call an impurity measure. And then we will discuss how to trim a decision tree. So by distinguishing pre-trimming and post-trimming. I will learn you how to read the decision rules issued from a tree, so how to read a tree, how to interpret a tree, and to implement a tree with Python. Okay. Okay, so don't hesitate if you have any question on the. You can ask me a question directly or on the chat. I'll put the chat on my right. Yes, it's okay. Okay, so what is the general idea of a decision tree? The general idea or principle of a decision tree is to partition the individuals, or for instance, in your training data set, into groups of individuals that are homogeneous with respect to the target variable y. Okay, so let us imagine that we have the binary variable y. Then my objective is to group together people who have for which we observe y is equal to 0 and people for which we observe y is equal to 1. Okay, and I want to group them according to their feature x. Okay, so I will use model feature x to group the individuals according to their target variable y. So if the target variable is continuous, we have a regression tree. And if the target variable is discrete, we have a classification tree. This partition is hierarchical hierarchical because it takes into account the relative predictive ability of each predictor. What does it mean? It means that, okay, to group together the individual of my training dataset, I will use several model features. For instance, I will just gender, the age, another variable, the income is whatever, and I will segment my population firstly by using a variable x1, and then in a second stage by using a variable x2, etc., etc. So we have a hierarchical partition of the individual of my training dataset, given a set of explanatory variables. Okay. What are the advantages and disadvantages of a decision tree? Decision tree have several advantages. The first is that, okay, they are good enough for a non-parametric model, a modeling of a non-linear relationship. Okay, it's really, we'll discuss this point later, but okay, this is a very simple model that could capture, for instance, what we call the threshold effect. Okay, the fact that, okay, an explanatory variable x has a positive or negative effect given the value of another variable, or if of x1 also, okay. We could also capture some interaction effect, the fact that x has an effect on y that depends on x2, for instance, okay. This method is also adapted to large databases, okay, both in the individual n and the predictor dimension, so p, okay, so I can use a decision tree with many individuals or with many model features. This allows to use quantitative and qualitative predictors. This allows to consider missing data, okay. I can late missing data in my dataset, and then the fact that there is some missing value for x1 will be considered as an information, and then we will have a decision about y in the case where there are some missing value of, in the x1 variable, for instance. Which a point that is related to the fact that it is a machine learning algorithm is the fact that, okay, this algorithm will automatically select the predictor. So I don't have to select which variable will have to be considered in my decision tree. The algorithm will select, for instance, 3 variables among a set of 10 variables in my dataset. This provides a hierarchy of the predictor importance. At the end, it is possible, for instance, to say that the age the age variable is the most important variable in my decision tree to explain, for instance, the default in my for my borrower. Okay. Now the drawbacks. The main drawback is that decision tree have limited predictive power. Okay, so for instance, if I use a decision tree for a regression, in general, it's difficult to reach a very high R-squared value, okay, for many datasets, okay. In general, it is also the same for classification. It is difficult to reach a very high IUC value for a classification problem with a decision tree. So why do we learn decision tree in detail? Because this model are the basis of some aggregation methods, such as the random forest or the boosting method, for instance, the XGBoost algorithm. And this drawback of the decision tree that, okay, this model have limited predictive power is a shortcoming by combining several decision trees, okay? And in this case, for instance, a random forest, it is a combination of several decision trees trained on bootstrap samples. And the fact that it is well known that, for instance, a random forest gives you very high R-squared value if you have a random forest for regression, or very high IUC value if you have a classification problem for most of the economic problem in general. Okay, that's why the random forest is one of the most often used ML algorithm in machine learning in economics and finance. And this is not the same, for instance, in computer science, in computer vision, and so on. Okay, but in economics and finance, it is one of the most often used algorithm. This is also the case, for instance, for the XGBoost. Okay. So what is the general principle of decision tree? So we have, this is an iterative algorithm. So we have several iterations. And for each iteration, the individual in the training sample are divided into several classes. In general, we consider only 2 classes. This is why we have a binary decision, okay? So at each step, each iteration, we separate all the individuals in my training data set into 2 subgroups, okay? For that, we use a variable. For instance, I use a gender. On the left, I have the woman. On the right, I have the man. I can also use, for instance, the income. For instance, on the left, I have all the people who earn less than 1,000 euros. On the right, the other, etc., etc. The division is oriented towards the prediction of the target variable. And the idea is to select the variable, the predictor, that leads to the best separation of individuals from the point of view of the prediction. What does it mean? It means I can separate my individuals with many variables, okay, with gender, income, etc. And for a given variable, for instance, income, I have many thresholds. I can put a threshold like 1,000 euro, 2,000 euro, etc. I choose the predictor, so the variable and the threshold value, such that I get 2 subsample or 2 subdivisions in which the individuals are homogeneous with respect to y. Okay, and the idea is to increase the homogeneity at each step, to increase the homogeneity of the individual with respect to the target variable. Okay. Each division in the iterative process defines subpopulations that correspond to the nodes of the tree. And the iteration, the operation is iterated for each node until no further separation is possible. Okay. And the last subpopulation or terminal nodes are often called the leaves of the tree. We have a root. I will define as a go back to the vocabulary, but okay, this is a general idea. So maybe it is unclear at this stage. So let me first introduce the terminology and then detail the way the binary division principle. Okay, so what is the terminology? We have a decision tree here in which we have first the root. This is a node, a decision node with no parent. There is nothing here, okay? This is the root of the tree. This is an inverted tree, okay? So we have the root on the top and the leaves, okay? Okay. So we have the root here, okay? Then we have some decision node. And for a decision node, there is a rule, okay, according which I have 2 subgroups. Okay, here I have a decision node. I have a subgroup here and a subgroup here, okay? This subgroup on the right is also a decision node because there is a split process here and two subgroups, which are the child nodes. What we call the terminal nodes. Here, this is a terminal nodes because there is no subdivision after this point. This is a final terminal node. This is a terminal node. So, okay, so everybody knows that I have an appointment with Catherine. This is a colleague. These terminal nodes are also called the leaves or the leaf. So we have decision node, the root, and the leaves. When I evoke the node ancestors, it corresponds to the parent, grandparent of a decision node, okay? Here I have a decision node, and here this is a parent node, okay? Okay, because this is a population from which the population which is here is issued from. The descendants of a node are the children, grandchildren, etc. Okay, so here I have a decision node. I have a rule to split all the individuals which are here, for instance, the gender, and here I have a child node on child node on the right and child node on the left. In the tree, I can identify some subtree. This is a part of my tree. What is how to define the distance between two nodes? So first, for instance, consider this decision node and this decision node. What is the distance? It is simply defined by the number of links between them. So 1, 2. So the distance between the root and this decision node is equal to 2. What is the depth of my tree, or the depth of my node, of a node in particular? It corresponds to the number of ancestors or distance from the root. So for instance, if I consider this node, what is the depth of this node? So 1, 2, 3, okay. It is the distance from the node to the root. And what is the depth 3? The depth of the tree, or the tree depth, it is correspond to the maximum depth that I can define in my tree, okay? So here, how to find the maximum depth? This is the distance between the root and this leaf, for instance. So the depth of this tree is equal to 3. 1, 2, 3. This is the maximum depth that I can define between a final node and the root in this tree. This is clear for the definition. So let me summarize. The root, a decision node, a terminal node or a leaf, and the tree depth are the main notions that we have to get in mind, okay? Okay, this is an example of a decision tree for a credit scoring model, okay? Each leaf, so each leaf here, is associated with a specific path, so from the root to the leaf, and this path corresponds to a rule, a decision rule, okay? Because in a final length, I take a decision about y. For instance, let us imagine that here, y, that my target variable is equal to 1 or 0. Okay. 1 if it's creditable. Okay. The borrower is creditable. Okay, I gave the credit, and 0 otherwise. So in each final leaf, I will take a decision. So if you are here, I give you the credit. If you are here, I don't give you the credit, for instance. So here, my prediction is 1. Here it is 0. It's clear? The path that allow a given individual to go from the root to this leaf is called, it is this path, okay? And this path define what we call a decision rule. What does it mean? It means that, okay, if my checking account balance is larger than 200 euros, if the duration of credit is less than 30 months, if the payment status of my previous loan is paid, then I forecast yes. I forecast that, okay, the borrower is creditable and give him the credit. It's clear? And just maybe I miss something. Each time I have a decision node here, and this is a condition. Okay, for instance, about the checking amount balance. If this condition is satisfied, I go on the left. If it is not satisfied, I go on the right. This is always a rule of thumb, okay? So on the left is yes, on the right is no. No, no, yes, yes, no, yes. This is a convention in decision tree, okay? No, yes. So at the end, I have a rule, for instance, if I have an individual for which the checking amount balance is smaller than 200 euros, then I go here. If the length of the current employment is larger than 1 year, this is yes. And then for an individual of this type, my prediction is 1. It's clear? So for each individual, I can, okay, associate a decision rule and forecast a value for him, okay, on the target variable. It's clear for you about the interpretation of what we have in a decision tree. This is a classification. In general, when you have a regression in the leaf, you have a value. For instance, here you will say y hat is equal to 20. Here, y hat is equal to 10.5. Okay. And so, given the decision rule, there is also a decision rule, and if I here, then I will forecast y is equal to 10.5 for all the individuals for which the checking account balance is larger than 200 euros. All the people for which the duration of credit is smaller than 30 months, also pay for people who have paid their previous loan. Okay. And then for all these people, I forecast the same value of 10.5. This is okay? So the question is how to build this decision tree. And you understand that there are 3 main challenges. The first is at each step, the choice of the division variable. Why I start with a checking with a banking amount, okay? Or the age, or okay, why I consider this variable in the first subdivision, okay? And then why in the second case I use the duration of the credit, etc. Okay, why choosing this variable at this stage? Why choosing this variable for the decision and so on? And a related question is a threshold. Why using a threshold at 200 euros? Okay. The stopping rule of the iterative process. When should I stop my division process? And and how to fix the forecast in the final leaf? Why I forecast a value 1 or 0 in a given leaf, or why I forecast a value of 20 if this is a regression in the final leaf. So to answer to these 3 points, we implement a given algorithm. So there are many algorithms to produce a decision tree. And one of the most famous is a CART, a classification and regression tree, proposed by Brayman and co-author in 1984. This is a reference of this paper. Okay. In general, if there is no no indication in, for instance, in a package Python, in general, it is a CART algorithm that it is implemented for a decision tree. But you have to check if it is a CART or the shade or whatever. Okay. So the CART, this is Brayman. Okay. The CART algorithm use the principle of binary division. And the binary division is performed using the predictor. So at each stage, we select the predictor, so the variable, with the highest discriminating power, which is measured by the variation in an impurity criterion. So the important term is the impurity criterion between 2 successive nodes. So I have a measure of impurity at a node, and then I have a measure of impurity in the child node. Okay, and the idea is to decrease the impurity of between 2 stages. Alors, first, let me introduce what is a binary division. It's very simple. I have to split my variables, my individual, into subgroups, but it depends if I use to split my individuals, quantitative or qualitative, binary or non-binary variable. Okay, so let me describe all this possibility. First, let me consider that I have a quantitative variable. Okay, I want to use, for instance, the income to split the individual. Okay, so here I have all the individuals, and then I want to split with a particular rule the individual according to their income. So let us imagine that okay, the variable is defined on R. We are searching on the support of the variable for the threshold value C that lead to the best partition. So in general, we order the variable, for instance, the income of all the individuals, and then we consider M values, for instance, 200, 300, 500, 900, etc. Okay, for the income. And then we consider M-1 potential division that I could produce by considering the income. And for each threshold, for each threshold C, I have a particular subpopulation here and a subpopulation here. Okay. So when I consider a quantitative predictor, there is a second related question, is the threshold that I have to use. And for that, I will consider M different alternative values of the threshold. Okay. In general, these M values are ranged between the minimum and the maximum of the series observed on my training sample. Okay. But I have not to be equal to the minimum or to the maximum, because in this case, I have no people in one node, okay, subnode, okay. If you have a binary predictor, this is really easy to operate a binary division, because in this case, okay, you just have to split the sample according to the value of the binary predictor. Okay, so if it is a gender, here I have the man, here I have the woman, and this is my parent node. Okay, so there is no difficulty. If my variable is multinomial, categorical, multinomial qualitative or categorical, for instance, if I have L modalities, then there is many possibility to group the modalities for a binary division. And mathematically, we have 2 to the power n minus 1 minus 1 possible divisions. Let me illustrate with a variable x, marital status, for which we have 3 modalities: married, divorced, single. In this case, I have 3 potential binary division. First, I can consider here the marital status. Each time is marital status, but I can say, okay, if it is married on the left, otherwise on the right, and then here I have the single and divorced, I can consider married and single on the left, divorced on the right, married, divorced on the left, single on the right. Okay, so with a 3 modalities variable, I have 3 potential alternative binary divisions. It is clear? Great. So now, whatever the variable that you consider, we will compare what we call the impurity at the parent node to the impurity at the child node. Okay, and what we call the impurity or the impurity measurement. So the best predictor for splitting a node is obtained by comparing the impurity measures obtained on the parent node and the 2 child nodes. So this is a mathematical definition. So let me start with the mathematical definition of what we call an impurity measure. So let me consider y, my target variable, taking S modalities. So in general, for you, let us simplify, for instance, with S is equal to 2, okay? Let us imagine that y takes only 2 values, 1 and 0, okay? But I can produce a decision tree for a classification problem in which y takes 5 values, for instance, 1, 2, 3, 4, 5, okay? But okay, let me reduce the problem to S is equal to 2. PT is a joint distribution of the target variable at the node T. Okay, so we have a distribution of y at a given node. So here, y as a given distribution. What is an impurity measure? Is a function phi defined from 0, 1 to the power s to r. So this is can be positive or negative. Where, sorry, it is r plus. The impurity measure is always positive or null. The impurity measure is minimum if there is a node for which the value of y are such that the probability to observe a given value, for instance, 0 or 1, is equal to 1. What does it mean? It means that at a given stage, for instance, at a given node, okay, all the people here are either 0 or 1. Then the probability that y takes a value 1 at this node is equal to 1. Okay? It is the same if I have only 0 people, okay? In this case, the node is pure in the sense that there is no mixture between 0 and 1. And then the impurity measure is minimum. On the contrary, the impurity measure is maximum if at a given node, the probability to obtain 0 or to obtain 1 is equal to 1 divided by 2, to 50%. So let me illustrate. If I have a node in which I have 4 individuals, 2 1 and 2 0, the probability to observe 1 at this node is equal to the probability to observe 0 at this node is equal to 50%. Then I have a perfect mixture between 0 and 1 on this node. Then the impurity measure is maximum. Okay? Okay, the impurity measure is also a differentiable function and is symmetric in the argument. This is clear? So,
sorry, can I
yes.
ask a question? Yes,
Yes.
in the previous slide, I didn't understand when the PT is maximum. No, the one after this.
Okay, here. Okay.
Yes.
It is maximum when the probability to get 0 or 1, if I have an example with 0 or 1. Okay. So if I have two modalities, 0 and 1, and it at a given node, I have the probability to observe 0, which is equal to the probability to observe 1. Okay. These two probabilities are equal. Okay. So at this stage, there is the same probability to observe, for instance, a default or non-default. And then we consider that with respect to the default, this node includes an impure population. Okay, and in this case, the measure phi, will be maximum. It's okay?
Okay, so basically the probability to be, for example, let's say black or white is
yes.
high. This
exactly.
is what, okay, yeah, now it's clear.
It is a measure of impurity. For instance, if I have a node in which I have a black elements in the impurity is low because all the people have the same Y value. If I have a mixture, then the impurity is high, and the impurity is maximum when the probability to observe black and white is equal.
Great, clear, thank you.
Fatme?
Excuse me. In the previous slides, you said that we choose the variable so that it is the most homogeneous with respect to y. Now, am I right that we use the most homogeneous and then choose the next most homogeneous? So we work our way toward heterogeneity.
Yes.
Am I right?
Yes. We compute an impurity measure at this level. We compute an impurity measure at this level, and the goal is to minimize the impurity or to increase the decrease in the impurity between the two stages. Okay.
So in the first step, we choose the most impure variable.
It's difficult to say an impure variable. Okay, it is. we compare all the variables and the threshold if it is a continuous variable, and we will use all these variables to separate the population. Okay, yes, for instance, I consider gender. I separate according to gender. I consider income with a threshold of 500 euros. I separate my population in two groups given their income. Okay, so I have two potential binary division possible. And I will compare these two binary division in terms of reduction in the impurity measures. And I will prefer the gender, to use the gender at a given node to separate my population if it allows me to reach more pure child nodes than if I use a separation, a binary separation based on the income. This is clear?
Yes, thank you.
I will discuss this point and we will do an example. Mireille?
I have just a question in the terminology. So when we are talking about modalities, we mean the leaves, the leaf, the
I have some difficulty to hear. Maybe it's the same for other participants.
leaves we
Could
have
you
under
use...
the decision node. So
I'm sorry, Mireille,
if we have
I didn't hear you very clearly. There is a problem of connection, I think. Could you use the chat? Yes, Bob. We lost Mireille. So I propose to continue, okay? And then I will answer to Mireille when she will go back. So there are different impurity measures that are proposed, for instance, in scikit-learn. The channel entropy, the Gini index, and the classification error, okay? In general, with the CART algorithm, by default in most of the software, the impurity measure that is used is the Gini index, okay, this one. What is the value? Let us imagine that S is equal to 2. It is simply phi is equal to 1 minus the probability that I observe y is equal to 0 at node t squared minus the probability to observe y is equal to 1 at node t squared. Okay, it's very simple. So if I have a pure, for instance, let us imagine in case in which I have only 0 individuals, there the probability to observe 0 is equal to 1. The probability to observe 1 is equal to 0. And so 1 minus 1, phi is equal to 0. Okay? On the contrary, if I have the same probability to observe 0 and 1, then this is equal to 1 over 2. Okay, this is equal to 1 over 2, and the entropy, the Gini index, sorry, is equal to y minus 0.25 minus 0.25 is equal to 0.5. Okay, and this is the maximum value of the Gini index in this case. Okay, so the Gini index range from 0, where there is a node is pure, to 0.5, where there is a maximum impurity. So the impurity measure is a diversification measure for a node. It's equal to 0 for a pure node. It takes a maximum value in case of equiprobability of the distribution of y. So here I have, for instance, a given impurity. And then my goal is to get, as most as possible, a situation in which on the left, I have no impurity. On the right, I have no impurity. And then if I compute my impurity measure here and here, then I have a large decrease in the impurity measure. This is clear for everybody? Great. So the objective assigned to the division of a parent node is to obtain child nodes with a lower weighted impurity than that of the parent node. And the objective is to select the predictors that maximize this decrease. This is a formula for what we call the impurity gain, where the impurity gain, delta of G, associated with a particular variable, for instance, gender, is the difference between the impurity measure at the parent node T and the weighted average of the impurity measures of the two child nodes. So here I have the impurity of my parent node, so the Gini index. Here I have the impurity measure on the left child node. Here I have the impurity measure on the right child node. NL corresponds to the number of individuals that are here. For instance, the number of men. And R is the number of individuals in the right child node. And NT is the number of individuals in the parent node. So what we have here is simply the weighted average of the impurity measure of the child nodes. And the impurity gain is the difference between the impurity of the parent node minus the weighted average of the impurity measure of the child node. It's clear? And we will compare the predictors, the variables, according to their impurity measure. Low information gain is the fact that we have a mixed a high impurity in the child node. High information gain means that, okay, we have low impurity in the child node, okay? So let me illustrate with the Titanic dataset, so a subset of the Titanic dataset. So Titanic dataset is a famous dataset that is used in machine learning, in which we try to predict who survived and not survived on the Titanic boat after it shrinks. I will consider, and we have a variable that it is to indicate if the person survived or not. And we have some characteristics, some feature X, so the class, the age, and the fare price, the fare. I propose to consider a very small sample of 5 passengers. 3 have survived, 2 did not. So this is my passenger 0, 1, 2, 3, 4. So I have 4 passengers. For each, I have the class, or third class, third class, third class, or first class, the age, the fare, price of their ticket, okay, and a binary variable that takes 0 if they did not survive and 1 if they survive, okay? And I propose you to build a decision tree for this sample. So how to start? So first, let me consider, first, I will consider the class to make the binary division. So I have two modalities for the class, so third class and first class, okay? So this is a binary variable, okay? And let me consider this variable and show what is impurity gain if I use this variable as a predictor for the first variable in the root of my decision tree. Okay, so let me consider a rule like this. So P class is smaller than 3, so it is true. So what does it mean? It means that here we are in the first class. And when it is false, we are in the third class. This is clear. This is a presentation of a typical, even for a binary. The software scikit-learn does not mention if x is equal to 0 or x is equal to 1. It states just if smaller than the highest value, and on the left it is true, on the right it is false. It is always the same. Clear? So let me start by computing the Gini index at the parent node. So we have 3 survive people, 2 not survive. So what is the Gini index at this stage? It is 1 minus the probability to not survive to the squared minus the probability to survive to the square. So what is the probability to not survive? I have 2 people amongst 5 who did not survive. So the probability is 2 divided by 5. What is the probability to survive? Is 3 divided by 5. So what is the Gini index on the parent node is 0.48. 0.48. This corresponds to the Gini reported in scikit-learn here. It's clear? What is the impurity on the left node? And so what is the impurity on the left node? As I said before, on the left node, we have all the people who were in the first class. So we have these people, and we have these people, this individual. So in this class, in this subpopulation, we have only 2 individuals. And the 2 have survived. No people did not survive. So what is the Gini index at this stage? On the left node, it is 1 minus the probability to not survive to the squared minus the probability to survive to the squared. So it is, what is the probability to not survive? It is equal to 0. And what is the probability to survive? It is equal to 1 because it is 2 divided by 2. So what is the Gini index? It is equal to 0. And here, scikit-learn report a Gini index of 0. Why? Because there is a homogeneous node. Okay, there is only people who survive. What is the impurity on the right node? So here we have the people in the third class. So we have this individual, and this one. So among the 3 people who were in the third class, only 1 survived and 2 died. So what is the Gini index? It is on the right node, it is 1, minus the probability to not survive, to 2 divided by 3 squared, minus 1/3 squared, and the Gini index is equal to 0.44. Okay, so we have the Gini index on the chi node, and then what is the weighted Gini index here? It's simply the weighted average by where the weight are defined by the relative size of the subpopulations. So the Gini, so this is the Gini of the left and the Gini of the right times the number of individuals on the left node divided by the total number of individuals, and on the right node divided by the total number of passengers. So I have 2 divided by 5 times 0 plus 3 divided by 5 times 0.44, and we have a weighted Gini index of 0.26. So what is the impurity gain if I use the class as for the binary division? I have a gain in terms of impurity that is equal to 0.48 minus 0.26, and it is equal to 0.21. This is a gain in impurity that I could reach if I use this variable for the binary division at the first stage. So now I have a loop on all the potential variables, all the potential threshold for the continuous variable, all the potential recombination of categorical variable, and each time I will compute the impurity gain. And then, according to this rule, I will choose the best predictor for the first decision node. This is what is reported in this table. So here I have all the potential splits that I can use. Remember that I have only 3 variables. I have the class, which is a binary variable. I have the age, which is a continuous variable, and the fare, that is also a continuous variable. For age, here I consider 4 threshold values. And for the fare, I consider 40, also 4 threshold values. For each of them, so for instance, so if I consider a split according to the age, given a threshold of 38, on the left node, I will reach a Gini index of 0.5. On the right, I will reach a Gini index of 0, and then a weighted average of 0.4. It's clear? If I use a class, this is a binary variable. On the left, I have this Gini. On the right, I have this Gini value, and this is my weighted Gini index. Question? What are the best variables for you that you recommend to me to use for the first split? Ah, yes, sorry. Okay. Up. What? Okay. What are the best variables that you recommend me to use for the first split according to this principle of binary division and gain in impurity measure? Obviously. So this is not the impurity gain, this is a weighted average, but the starting point is the same because, okay, we start with 0.48 for the Gini index at the parent node, okay? So I don't have to compute the Gini index, I have to minimize the weighted Gini on the child node, okay? It's clear? And delta G is equal to 0.48, sorry, minus this value. Okay. So in order to maximize the impurity gain, I have to minimize the weighted Gini. Okay. So where the Gini weighted Gini is minimized, it is minimum for when I use the fare and I use a threshold of $53, and it is also, this is exactly the same value. So I'm neutral between choosing fare with this threshold and the class. And with the class, if this is a binary variable, so there is no threshold issue. And so I obtain the same impurity decrease. So I can use one of them. There is no particular reason to privilegiate one over the other. Okay. But this will be my first variable for the first node. And then, okay, I will use here, for instance, the class. On the left, I have the first class. On the right, I have the third class. And then here, for all the people in the first class, I have to choose the second variable for the decision node and to rank them, to split them, etc. This is the same for the right. So I have to redo all this exercise for each decision node at each step in my iterative procedure. It's clear for? Do you have some question? Okay. So at the end, we have a given decision tree. For instance, let us imagine that we have a decision tree like this. And at the end, let us imagine that we stop here. So we have final leaf, final decision node, final node, terminal node or leaf, whatever. And so now we have to assign a label to each leaf. So what is the value of y if my individual is here, or what is the value of y if my individual is here or is here, okay? In general, in case of classification 3, we use what we call the majority class prediction. This is very, very simple. It corresponds to modalities that let us imagine, let us remember that, okay, we have S is equal to 2. So, okay, S and minus, okay, and S is element of 0, 1, for instance, okay. Y takes two values, 0 and 1. And what is the modality is that you forecast in a given leaf, it simply corresponds to the modality that maximize the probability to observe a given value of y in this leaf. Okay, so what does it mean? It simply means that, okay, if I have a leaf in which I have 2 1 and 1 0, what is the prediction given by the model for all the individual in this leaf? It will be 1, because this is a majority class that I have in this leaf. Okay, this is very simple. So if I consider a new individual, which is not in my training sample, and given its feature values, this individual is classified in this final leaf, then I will forecast y hat is equal to 1 for this individual. Okay. So let me summarize what is the information that are reported with scikit-learn. We have this type of information with Python. So we have a node and a splitting rule. Here, this is based on gender. Gender is equal to 1 and 0. So if it's equal to 0, we are on the left. If it's equal to 1, we are on the right. Here, I have another decision rule based on the age. If the age is under 13, we're on the left. If it's over 13, we're on the right. Here, we have a decision rule based on the class. If the decision rule is equal to class 1 and 2, we are on the left. If the class is equal to 3, we are on the right, because you have 3 classes in the sample. Then, for each node, whatever it is a decision node or a terminal node, we have the Gini index. We have the Gini index here. We have the Gini index here. It's clear? For each node, whatever it is a decision node or a terminal node, we have the number of examples in the node. In this node, we have 887 individuals in the root node. Here we have 314 individuals, and here we have 117, 144, etc., etc. For each node, you have the number in the binary case. We have the number of individuals for which, for y is equal to 0 and for y is equal to 1. And here, by design, you have the number of 0 and the number of 1. by design, not by design, but in general, the number of 0 is on the left, and the number on the right is the 1 is on the right. Okay. So among the 887 individuals, we have 545 who survived, who didn't survive, sorry, and 342 who did not survive, with y is equal to 1. This is exactly the same here for each node. Whatever it is a decision node or final leaf, we have also an information about the majority class vote. If I stop at this stage of the tree, this is not possible, but okay, let us imagine that I stop at this stage of the tree, then the majority class is 0. And so what is the prediction for all the individuals who belong to this class is the fact that they did not survive. But this is not interesting if you consider decision node, but where are the final nodes? So the final nodes is here, 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 and here. So if you are in this group, the prediction of the model is that you survive. If you are in this group, the prediction is the model is that you don't survive. Why? Because here, the model predicts that you survive because for the training data set, among the 41 individuals that follow this decision rule, then we have 33 people who survived and only 18 people who did not survive. And so the majority class is 1. And so the model predicts that, okay, you survived. Here, the model, if you reach this group, the model predicts that you will not survive. If you are classified in this group, the model predicts that you survived. And here, what is the prediction of the model? And do you think that it's okay? In this case, okay, we have a 50-50, okay, situation in which we have 144 people, 72 survived, 72 died. And so what is the prediction in this case? By convention, the model predict 0. Okay, this is a convention. Okay. So let me let me consider a case. So just gender or sex. Sex is the name of the variable, but it is gender. But okay, if I remember well, it is 0. If I remember well, it is 0 for 0 for women and 1 for men. So given this model, what is, according to you, the prediction for a woman of 32 years and class 1 with a ticket in the first class? So what is the prediction? What is the Y for a woman of 32 years that was in the first class? Nobody wants to predict the issue for her? Yes, Fatme?
I think first she's a woman, so we go to the next node, which is true, and then she's 32 years, so she will not survive.
Sorry, sorry, I made an error. So Fatmi said that, okay, she's a woman, so on this node, this is true. We are on the left.
We're on
she
the
has
left
32 years, so we are on the right because this is false. Okay, so this condition about age is false, so we are on the right. So this woman is classified here, and for her, unfortunately, the prediction of the model is that she will not survive. It's clear? Great.
Yes.
So the information for about the class is not necessary for her. This is not the same, for instance, if you have a man, because in this case, the class will be determinant in the survival probability. But for the woman, as you observe, the model first selects the sex, first the gender, then select the age, but the class is unimportant to determine if the woman live or not. Okay. Congratulations. So last point, there is a color code with scikit-learn. By design, by convention, orange node is when you have 0, so not survived, and blue node is 1. So blue is 1, orange is 0. Okay. So here I have a leaf in which the model forecasts 0, so not survived. So this is in orange. This is also you see here and here. Okay. On the contrary, we have 3 subgroups in blue, decision nodes in blue. As you remark, there is some differences into the color orange that is used by the scikit-learn, because there is a second color code, which means that the darker the color, the higher the probability associated with the majority event. What is the probability? So let me now define what we call the probability. So we have 3 groups, or here, this group, for instance, in which we predict that, okay, people will survive. What is the probability to survive? Let us imagine that, okay, y is equal to 1. If you survived and 0 otherwise. What is the probability here to survive or to not survive, whatever? Let us consider, for instance, to survive. Given that you are here, okay? This is simply defined by 86 divided by 532. Or in the same, okay, the probability to not survive is equal to 446 divided by 532. This is approximately, I guess, at 0.9. Okay, 0.8. So this is a high probability. This is why the color here is dark. And the contrary here, the probability to not survive is equal to 545 divided by 887. This is approximately equal to 0.5. Okay, so the probability to not survive is lower here than here. This is why the color is darker here than here. This is the same for the blue color. Here, the probability to survive is higher than here. Okay, so you have an indication with the color and with the darkness of the color. Okay. And here, this is a very particular case because, as I mentioned before, there is an equiprobability to survive or not. And so the model does not know if it's orange or blue. So the color is, there is no color. Okay. So this is, I will conclude here. This is an example of a random decision tree of classification with a data set based on iris flower data set, which is a data set that consists of 50 samples of 3 spaces of iris. So Y takes 3 modalities, so 1, 2, and 3. And in this model, there are 4 features. So the length and the width of the sepal and petals in centimeters. Okay. And this is the final decision tree of classification for this example. And you observe, okay, that at each step, you have the genie, the sample, the value, the class. 1, 2, and 3. This is a setosa, versicolor, or virginica. This is the 3 types of iris. And then, given the value of the feature, so the length and the width of the sepal and petal, you have some decision rule that allows you to predict if the flower is of type of iris setosa, iris virginica, or iris versicolor. This is clear? Okay. So I propose to take a break of 10 minutes. If there is no...
Could I have a question?
Oh, yes, yes, yes.
When we get Gini more than 0.5, because the first box we have 0.67 approximately.
Yes.
So when we get this case,
when we, sorry?
When we get the Gini, it's more than 0.5.
Sorry, I have a problem with my screen in the same time. I have a strong, sorry, a strong problem with my up. Okay. Just could you repeat the question, please, because I made something else in the same time.
In the flower example.
Yes. Yes, I have a problem to reach the flower example. This okay. This is I reach.
Yes. Okay. The first box we have
yes.
Gini.
Yes.
Was 0.67.
Yes, because this is an I said you that the maximum value of the Gini is equal to 0.5, but in a classification problem with 2 modalities with a binary target variable. So in my example, Y takes only 2 values, 0 and 1.
Yes.
And here, this is a classification problem in a categorical variable with 3 modalities. So Y takes 3 modalities, iris setosa, iris virginica, and iris versicolor. Okay, and the maximum value of the Gini index in this case in 0.66.
Okay.
Because it is 1 minus 1/3 squared minus 1/3 squared minus 1/3 squared, and this is equal to 0.66.
Okay. Thank you.
Other question? No? Okay, so I propose take a break and then see you in 10 minutes. Okay. If everybody is here, I propose to resume. Great. Okay. So this is a second example. We have I previously show you an example of classification decision tree or classification tree for a classification problem with 3 modalities. This is the example, another example of the outcome of a regression tree. So we have a decision tree regression model, and this is the outcome. And the outcome, this is, okay, the prediction of y issued for a model with a maxep is equal to 5 and the maxep is equal to 2, whatever. And this is the data, the training data set. Let us consider, for instance, the model with maxdep is equal to 2. Okay, so what does this is this type of output that we obtain? Why? Because, okay, we have a variable x1, okay, x2 possibly, or x3, and then we have this type of model. Maybe there is no split on the left or no split on the right, but okay, at the maximum we have 1, 2. This is the depth of my model with max depth is equal to 2 here. Okay, so how many different values that I can obtain with the decision tree with depth equal to 2? Here, the model will give me a value 1, a second value 2, a third value here, and a last value here. So we could obtain 4 different values in the 4 potential different values in the 4 leaves. This is why we have 1 value here, 1 value here for y. Y is on the y-axis here. Okay, 1 value here and 1 value here. So we have 4 different values. And according to the value of x, okay, x is not represented. This is not x here. This is only the data that are represented. And given the value of x, well, we have some, here we forecast this value, this one, or this one. How this value is computed, how y at 1 is computed, is simply y at 1 simply correspond to the mean of the value that are here in the final leaf here. So for instance, if I have 3 values here, 3 observation and 10, 20, and 30, then, okay, then the forecast is simply the mean and is equal to 20. Do you have some question about the regression? And here, this graph illustrates the fact that when you increase the depth of the tree, then the number of potential values for y increases, okay, and is, I don't remember the number, but remember that when the depth is equal to 10, okay, we could obtain 1024 different value for y. This is the example that I gave you yesterday. But what does it imply? It implies that in this case, we have a step function which is very particular, and then we take some value which are very specific to capture particular point, and this is related to what we call the overfitting. In the fact that, okay, this model will be really good in sample, but maybe out of sample will have a very low forecast or very high forecast error. Yes, Samal?
Hello again. I wanted to ask, you said that when we increase the depth of the tree, the number of potential value of y increases.
Yes.
This means that it's better to decrease the depth of the tree?
Okay. Remember that the depth of the tree is considered as an hyperparameter, and we have to determine an optimal value for these hyperparameters, such as to minimize a cross-validation error and to avoid the overfitting. But we know that if the the depth tree decreases too much, for instance, if I have a tree with only one a depth equal to 1. What does it mean? It means that, okay, this model is only able to produce 2 values.
Yes, this means that it's not representative of the model if I want to explain something, right?
Yes, exactly. On the contrary, when the depth of the tree is too large, I have potentially a large number of forecasted value of y, and these values are capture some very specificity of the training sample. And this is not sure that, for instance, this type of point, this type of outlier will be present in the test set. And then this model may be not accurate, not adapted to new data for the training set. And so between a depth of 25 and a depth of 1, there is an optimal depth which related to an optimal complexity of the tree that allow me to have a good in-sample R squared, but also a good R squared for new data on the test set. And this is the idea to minimize the divergence between the R squared in sample on the test set and on the train. Okay, and I have to fix the depth tree such as to minimize the difference between the in sample and out of sample predictive performance of my model. Okay.
Okay. Thank you.
Okay, so let me now consider the final point is a pruning. Okay, so the idea is to control for we know that you can decision tree can overfit if it grows too deeply and capture even minor detail from the training data that might not arise when to see unseen data. This is exactly what we said before. And there is a risk of overfitting and lack of generalization. And this is why a solution, so there are many solutions, okay? The first solution that I present to you is to fix the optimal size of the tree, depth of the tree, with a cross-validation approach. But there are also alternative approaches to control for overfitting that are known as pruning. Okay, and we have 2 types of pruning: pre-pruning, post-pruning. Okay, the pruning is the fact that to cut a part of the tree. So pre-pruning, this is related to what I mentioned as hyperparameters. Pre-pruning tackle overfitting by stopping the tree from growing further when certain stopping criteria are met. So I will put some stopping criteria on the tree, on the form of the tree, and these stopping criteria are considered as the hyperparameters of the tree. Okay. This is not exactly the depth of the tree. I always say that the depth of the tree is the hyperparameters. In general, we control for the value of the stopping criteria on the following point. And the first is the maximum depth. This is an hyperparameters that set a limit on the maximum number of depth maximum depth of the tree. Once the tree reaches depth, so the algorithm, binary classification, division of the CART algorithm, stop. Okay? So when you will use scikit-learn in a few minutes, okay, you have scikit-learn decision tree classification, and then you have, for instance, max depth parameters. This max depth parameter is an hyperparameter that controls the stopping rule for the depth of the tree. Okay. This controls the maximum because, okay, the depth of the tree can be smaller than this value. Okay, let me go back. So I will say, for instance, the maximum depth is equal to 3. It means that the iterative algorithm of CART will go further, will iterate until the depth of the tree will reach this limit of 3. This is clear? You could also control alternative elements of the tree. And for instance, you could also control for the minimum sample split. Okay. This is the idea that, okay, I will control the number of samples of examples that I have in a split before to decide or not to decide to split it. Okay. And this specifies the minimum number of data points required in a node before it can be further split. This is an alternative to control the maximum depth. Okay, I require, for instance, 50 individuals in a node to decide if I can continue or not to split it and to determine some shine nodes. Okay, this is a constraint on the way that the tree is growing. You can also consider a constraint about the minimum sample leaf. That is, okay, I impose that the final leaf will include at the minimum, for instance, 10 or 50 observations. This is to avoid the fact that, okay, I can define a leaf in which I have only one individual, for instance, Christophe Hurlin. So I have a model, I say, okay, I have someone who are 50 years, who is professor at University of Orléans, and then, etc., we have many decision rules with many variables that allows the model to identify only one person. Why this is related to overfitting? Because there is a probability to observe the same person in the test set is very low. And so if I define final nodes in which I have few people, it means that my decision tree has a very large depth, and so it tends to isolate some particular points. Okay, so in order to control for that, I can put a minimum constraint on the sample leaf, on the minimum point that I should observe that each leaf should contain. You could also put a constraint on the maximum leaf node. This direct constraint on the number of leaf nodes in the tree, and a minimum impurity decrease. Okay, you allow a split if the decrease in impurity reach a given threshold. Otherwise, there is no split. Do you understand that all these constraints that we will observe here? We have a minimum sample split, the minimum sample length, the max depth, the max leaf node, the minimum impurity decrease. My way to proceed is the fact that I explain you all the theory required to understand all the option of the scikit-learn function that is required to run, for instance, a decision tree. Okay. So did you understand all this of this constraint? And do you understand that these constraints are related to the complexity of the model, because they allow to control for the complexity of the model and then to allow for the overfitting issue? Okay. And then, for instance, we will use a cross-validation procedure to determine the optimal maximal depth value that I can impose to my model to get the best decision trees that avoid overfitting, but allow me to have a good in-sample performance. No question about what we call the pre-pruning. So even if you don't do a cross-validation, okay, we can put some constraints on the maximum depth, the minimum sample speed, the minimum sample lift, the maximum lift nodes, or the minimum impurity decrease. In general, we choose only one criteria because all these criteria are sometimes redundant in the fact that they control the same things, the complexity of the model. And in general, people often control only for the maximum depth. Okay. But this is not a general rule, and you can control for the three. The alternative approach to control for overfitting is to let the tree growing and then ex post to make what we call a post-pruning. Okay. So we've put no constraints on the model. Okay, so if I put no constraint, for instance, in most of the cases, I will have a very complex, decision tree with many nodes, etc., etc. Okay, and then we will see if it's possible ex post to improve this model by cutting some part. Okay, and we will compare some subtrees obtained with the initial tree by removing some subtrees, some section of the tree. And we will see if by removing some section of the tree, we improve, we reduce the complexity of the model, and then we will see if there is an impact of the accuracy. And if the impact of the accuracy is moderate, we will prefer to a model which is pruned in the sense because we limit the problem of overfitting. Is this clear? So let me explain you how it works, and then you will understand all the options that are available in scikit-learn. So for that, we have a cost complexity pruning parameter, the CCP, which is called the CCP alpha in scikit-learn, to control the severity of the post-pruning. Okay. Higher values of CC alpha leads to more aggressive pruning. So you will cut several parts of the trees ex post to improve your model. If you put a low value of CC alpha, if I put 0, then the post-pruning model will be strictly identical to the pre-pruning model. What is the idea? The CCP evaluates the impact of pruning each subtree by considering both the cost, so the reduction in impurity, and the complexity, the number of leaves that have been removed. And the idea is to choose the best prune tree. Okay, so this is to choose best model with some subtrees, some parts which have been removed. So let me explain how it works. Let us imagine this is an initial model on the left. Then ex post, once this model has been trained, I will consider to remove this part. I have a pruned model, and I will compare these two models in terms of complexity and in terms of accuracy or decrease in the impurity. And I have a weighted objective between decreasing the complexity, but if I decrease too much the complexity, my accuracy will be lower, or my decrease in impurity will be lower. And so I have a trade-off to find. And this trade-off is controlled by the CC alpha parameter. And I will compare these two models with two criteria, complexity and impurity decreasing, or accuracy. It is approximately the same idea. And if this model is better, I will choose this model at the end. And then I have run a very depth tree, and then pruned it in order to an improved model to limit the risk of overfitting, especially. So how it works? So you compare, you prune a tree to avoid overfitting. You have alpha, which is a CC alpha parameter. This is a positive parameter, a complexity parameter. And then you compare. So let us imagine that you have your tree here. Okay. Okay. And then let us imagine that I want to withdraw this part. Okay. Then I compute the misclassification rate in the terminal node here. Okay, so I consider the remaining part of the tree, and I compute an accuracy measure. For instance, if it is a classification problem, I will compute the number of the percentage of correct classification. Okay, when I use the model without this part. This is this part of the equation. Plus alpha, my term that control for the trade-off between complexity and accuracy. And the absolute value of T tilde is the number of terminal nodes. So I compare, for instance, this model with this one. Okay, so the initial model. So how many nodes, final nodes I have here? So I have 1, 2, 3, 4, 5, 6. So I have 6 terminal nodes. And here I have only 4 terminal nodes. Is clear? So this model on the left is less complex than the model on the right. But now the question is to know what is the accuracy. Let us imagine that it is a regression model. We compare the MSE, mean square error, of this model and the MSE of this model. Okay. And what is the goal is to compare MSE alpha, which is the standard MSE of your model, plus alpha times a parameter that control for the complexity. And then, what is the optimal model? The optimal model is, in general, this is RT is the MSE for a regression model, and RT is the percentage of correct classification in the case of classification tree, whatever. What is the optimal model? Sorry. The optimal model is a model that minimizes this cost complexity measure or criteria. And for instance, maybe this is this model, which is the best. So this is the initial model less than this part of the tree. And the algorithm will consider all the variation of the initial tree by removing some parts in the tree, and then decide what is the best pruned tree model. So let me ask you if you have understood. So this is alpha, so the cost complexity risk parameter, so this CCP alpha, this is this alpha parameters, okay? And here, this is, okay, alors, let me consider this graph first. So this is alpha, and this is the depth of the prune tree. Let me, could you understand this graph? If I put a value alpha equal to 0, then the depth of the tree is equal to 8. If I ask, now I want to penalize, I want to introduce an alpha positive parameter to say, okay, I want to make a post-pruning. Then the algorithm will compare the initial model to sub-trees in which we remove some part, and then determine the optimal parameter with the previous criteria. If I fixed a value, for instance, of alpha at 0.05, the optimal model is a model with only a depth equal to 4, because some parts of the initial tree have been removed, and then we increase the cost complexity criteria. And the more I increase alpha, and the less is the depth of the tree, of the optimal tree. This is a number of, this is the same graph. We have alpha and the number of final nodes. Initially, we have 30 final nodes in the tree. If I increase alpha, then I obtain a pruned tree in which the number of final nodes will decrease. And for instance, here we have maybe 3 or 4 final nodes. This is, we see that when you increase alpha, you decrease the complexity of the model, but there is a cost. When I increase alpha, here I have an impact, there is an impact on the total impurity. The total impurity is a decrease of the impurity measure at each node of the tree. Okay? This is a kind of a measure of accuracy, because, okay, the idea is to decrease the impurity from the node to the terminal left. And so this is the sum of the decrease of impurity at each stage of the model. Yes?
So this is the same thing as the trade-off between bias and variance that we mentioned in
exactly.
days.
And so if you increase alpha, you have a less complicated model, and this less complicated as yes, exactly, because it does not reduce so much the impurity. Yes.
If alpha is equal to 1 or exceed 1, what happened?
No, in general, alpha is positive parameter, and when you increase too much alpha, the model is too penalized, and then the okay, there is no tree, as you can see here, for instance, as a if alpha exceeds 0.0.3, then the depth of the tree is limited to 1, so there is no tree. Okay. In general, it is very sensitive to alpha. It depends on your data set, but you will try to choose alpha. Okay.
So it's fair to,
yes.
to be between 0 and 1, right?
Yes. Theoretically, this is between 0 and 1.
Okay. Thank you.
And here, why we how can choose the alpha? You can make a cross validation, as I show you, but we can also have an interpretation in terms of overfitting. Okay, here we have alpha. Here we have the accuracy. The accuracy is the percentage of correct classification. We have a binary classification model, okay, and we just have the frequency of cases in which we well predict Y, okay? And so we have on the train set and the test set. So on the train, if I increase alpha, I decrease the complexity of the model. And so I have a decrease of the accuracy. But on the train set, when I first increase alpha, it increases the accuracy of my model of the train set. Why? Because initially, I have a very a model which is very complicated. It's clear? When alpha is equal to 0. This is a reverse way of thinking compared to the pre-pruning. Donc initially, I put no constraint on my model. So model is very, the depth is very large. For instance, the depth is equal to 30. Model is very complicated, okay, when here, because I put no constraint. Then I start to put a constraint on the complexity. So, okay, for instance, this part will be removed. So I have a less complicated model, and this less complicated model on the test sample increases the accuracy of the test sample because it reduces the overfitting issue. And so the optimal value of alpha is here, okay? And here I recommend to use alpha, which is equal to 0.01. It's clear, the pre-pruning. Pre-pruning, I control for the max depth. I will use a cross-validation approach. The post-pruning, I let the model rules, and then I fix a parameter in order to reduce the complexity exposed of the model. Is it clear for you, everybody? Okay, so there is a theoretical discussion about post or pre-pruning. Okay, so I have no particular point of view about this debate, but okay, we in general, okay, the post-pruning is very difficult to implement in practice because it requires a huge computation time. It takes, because when I have a very complex tree, there are many combination of subtrees that I can prune, okay? And so it is really difficult to implement in practice because when I have a huge data set, it takes a very long time to make a post-pruning approach. But if you have a small data set, okay, it can be interesting, okay, to compare to pre-pruning, but you have to try. In general, people, 90% of people use a pre-pruning approach because they didn't understood what is a post-pruning. Okay, this is my guess about the fact that okay, people use pre-pruning, but if you have understood, you can run the two type of pruning and to see how it works. My objective was to give you the foundation, the basic approach, just to understand the documentation that is provided by scikit-learn. Scikit-learn is a well-known package to do machine learning. It is one of the most famous packages to do machine learning. And there is a documentation. And my goal was to give you the opportunity to understand only the documentation and the options that are provided with scikit-learn. So this is, but you will understand, this is exactly what we have done together. So we have a training vector, X, a label vector, Y, and we compute a decision tree. Let the data at the node M, represented by QM with NM samples, for each candidate split. What is a candidate split? It's a couple GTM. What is G? G is a number of the features. So I have, for instance, the gender or the income, and I have a threshold TM, for instance, 800. I partition the data into a node on the left and a node on the right. What is the definition mathematically? QM left. So this is a child node on the left, where I have all the observation XY for which XG is smaller than the threshold TM. And QM right is the parent node QM less all the observations that belong to the left node. The quality of a candidate split of node M is then computed using an impurity function. Sometimes the impurity function is called a loss function, H, and the choice depends on the task, classification or regression, but whatever, we have a weighted impurity, which is the impurity on the left, the impurity on the right, and the weight corresponds to the to the relative number in the left node and right node. Select the parameters that minimize the impurity. So I select the theta. So theta, what is theta? Theta is the variable and theta is the threshold. So I select the variable, I select the threshold, such as to minimize the weighted Gini. And then recurse for subset on the left, on the right, until the maximum allowable depth is reached and M smaller than minimum of samples, or NM is equal to 1. This is the parameters by default. So there is no constraint on the depth, no constraint on the minimum sample, and no constraint on the minimum number of individual in the final leaf. If you don't put a value, so okay, scikit-learn will let the tree grow until it is possible, and even if you have only one individual in the final left, etc. Do you have some question? I hope now that you can understand all the details of the documentation of scikit-learn. Okay. There is also an information about the minimal cost complexity pruning. I used exactly the same notation just to facilitate your interpretation. But okay, the minimal cost complexity pruning is an algorithm used to prune a tree to avoid overfitting. This algorithm is parameterized by alpha, known as a complexity parameter. Alpha is not comprised between 0 and 1. It's just a positive parameter. Okay, there is no constraint on the higher value of alpha. Okay, and RT is a conditional, and then okay, you have what I defined before. It's okay. So before to go to scikit-learn, to collab and to apply with scikit-learn. So with Python, we'll use the package scikit-learn. In the package scikit-learn, we have a function which is decision tree classifier. Okay, and we have some options. I will show you how to implement them, but okay, just to understand, to know if you have understood all the options. So first, we have a criterion. We have 3 possible criterion: Gini, entropy, log loss. This corresponds to the 3 impurity measures that I presented to you. By default, the the criteria is a Gini because the implemented algorithm is a CART one. You have a splitter best and random. The strategy used to split at each node, the best choose the best split and the random choose the best random split. This is okay. This is just a way to accelerate the computation, because if I use the best, the algorithm will consider all the variables, all the potential threshold. There is a loop for all the at each node. At each node, we have a loop of all the potential variables, all the potential threshold value. If you want to accelerate, but there is a risk that you miss the optimal value, okay? You can use a random selector, and so you will select some variables. For instance, I will use gender, income with a threshold at 800, and I don't know, the age with a split at 32. And I will only consider these three variables, these three choices, to compare and to determine the optimal split. This is what we call the random. So this is just a way to accelerate the computation of your decision tree. It's clear? Max depth, the famous max depth. This is the maximum depth allowed for your tree. If you put no value, by default, there is no value. Minimum sample split. If I have a node and I ask, if I impose a minimum number of samples of individual to make a split, by default, the value is 2. Yes, to make a split, in general, we have to be 2 at least. But I can increase it. And by increasing this value, I will limit the depth of the tree. Minimum sample leaf. This is a minimum number of individual of sample required to be at a leaf node at the end. The minimum, if I let the choice by default, this is equal to 1. So maybe in one final leaf, I have only Christopher. Okay. What is the consequence of that is the fact that maybe this leaf will be not representative of a new data set, and so maybe I have to control, so either by the max depth or by this constraint, the general form of my decision tree. Max feature, I will explain this later because it is related to other things. I don't have the time. CC alpha, this is the parameters that you have to impose if you want to make a post-pruning approach. By default, it is equal to 0 because software privilegiates a pre-pruning approach by control of. But be careful. If I put no option on my max depth, mid sample, etc., and if I put no value to CC alpha, there is no pre-pruning and no post-pruning. There is no pruning at all. And the risk is the fact that I will have a decision tree with a huge dimension. So let me summarize. You know what is a regression tree. You know what is a classification tree. You know that the best, the well-known, most famous algorithm is a CART proposed by Breiman. This CART algorithm is based on the binary splitting principle. You know what is a root. You know what is a decision node, what is a terminal node or a leaf. You know what is a subtree. You know what is the depth, the tree of the depth. You know what is the impurity measure, Gini, channel entropy, log loss. You know what is the gain impurity. and the logic of the algorithm, and you know what is the pre-pruning or the post-pruning approach. Okay. So I have two solutions, but okay. So I propose to run a count. I have a count, and then I will start with Google Colab. And if you want, you can also take a break. So what is your preferred order? You want to go directly to the count for the theoretical part, and then take a break and just start for the collab? Okay. Let's go. So let's go with the count to okay, this is a count devoted to the validation, cross-validation, and to the decision tree. Okay, 21 participants, maybe it's okay, or I'm waiting a few seconds. Propose to start. Let's go. So cross-validation and decision trees. So true or false, cross-validation reduces the risk of overfitting. Yes, this is true. The goal of the cross-validation is to fix the hyperparameters, such as to reduce the risk of overfitting. True or false? Cross-validation is used to find the value of an algorithm parameters. This is false because we don't have to make a confusion between parameters and hyperparameters. The cross-validation is devoted to fix the optimal value of the hyperparameters and not the parameters. Just let me go back to the decision tree. What are the hyperparameters? The hyperparameters, for instance, is a depth tree. What are the parameters? The parameters are, you know, you remember in the documentation of scikit-learn, they denote the parameters theta. Theta are the threshold and the variable. The variable is strange to say that it is the parameters, but okay, they say that it is the parameters. Okay, but okay, let's consider, for instance, the threshold for the revenue. What is the value of the threshold? This is determined automatically by the machine learning algorithm. Okay, but me, I have the control on the maximum depth. Okay. One of these methods is not a cross-validation method. Yes, great. The three main approaches of the cross-validation are the hold out, the leave one out, and the scaffold approach. For hold out validation, the sample is split into three parts. Which sample does not exist? Perfect. In the hold out validation, we have three samples: train, validation, test. What are the terminal nodes of a tree called? What is the name of the terminal nodes? Okay. Okay, this is the leaves. The leaf. True or false? The CART algorithm by Breimann uses a binary division scheme. This is true. Breimann CART is based on the binary division. True or false? Binary division looks for the predictor that most increases the impurity between a node and its child nodes. This is false. Indeed, the idea is to decrease the impurity. True or false? An impurity measure is 0 if all the examples in the node belong to the same class. Great. This minimum, in general, the minimum value of the impurity measure is equal to 0. One of these measurements is not an impurity measurement, an impurity measure. This is the log likelihood. The correct likelihood is the temperature measure. Okay, great. So this is a podium. So congratulations to Kais, Ahmed, and Reda. So with Reda, okay, Reda Lamza. Okay, congratulations. So whatever the podium, I observe that globally you have understood the main concepts, and so now we have to implement them with Colab. So maybe I propose to take a break of 10 minutes, and then I will show you the first way to proceed with Colab. And then next week, we will work on Colab more deeply to apply the decision tree and then to apply your random forest, etc. Okay? So I propose to take a break of 10 minutes. It's okay? So see you in 10 minutes. Okay, let's go for the last part of this session. So now we will start with Python and Colab. So this is always difficult to teach with the software online. So this evening I will just try to familiarize you with Colab, but I will not have the time to run the first estimation of the decision tree this evening. But just to familiarize you with the use of Colab, and with Colab we will use Python, and we will produce some notebook with Python. So I hope that you have some basic notion of Python and what is a Jupyter notebook. And this is not the case. I will give you the very basic commands to import your data. This is really easy. And to run a decision tree. And the main advantage with Colab is the fact that you don't have to install Python on your own computer, and you will run Python on the cloud, and you don't have to be to have some this avoids all the problem with the Python version, the version of the packages, etc., because okay, this is really easy to have the latest version of Python. You don't need to manage this port by using Colab. Okay, if there is a limitation, but you will read on Colab what are the limitations to use Colab. But okay, to reach this limitation, you have to run a very important model with a huge data set, etc. So, okay, in general, in economics and finance, it is relatively easy to use Colab, even the free version of Colab, without reaching the limit. Okay, so let me start. So Colab is really easy to reach. So you type Colab, C-O, okay, Colab on Google, Colab, okay, Colab research, and then you have to log yourself. So here I am logged with my Google account. And then once you are logged in, you reach this web page with some information about Colab. I recommend you to make a tour of Colab and to read the video to understand what is Colab, how it works, etc. But okay, The point is the fact that there is a link between Colab and your Google Drive. So here I can switch from Colab to my Google Drive by clicking on the logo of Colab on the top left of my screen. So here, there is a link between Colab and my drive. So I can put some file on my drive and then run them with Colab. Okay, this is one advantage of Colab. So, okay, let me start, for instance, with a new notebook. Okay, if I want to write a new notebook, so then I click here on File. This is in French here, but okay, I think that you will understand. And then in a Python notebook, I can write some Python code and also to write some comments in Markdown. So this is a type of Word. So for instance, I can introduce a text. Okay, up here, bonjour, okay, hello, okay, and then, or before, I can introduce a code. Okay, so print. Okay, hello, and then you can run the code by clicking on this symbol, and then you get the result of your code here in the bottom of your code box. So I can introduce another code. Okay. And then run my cell. Okay, so it is possible to run cell by cell or to run all the cells. Okay. This is the main idea of Google Colab. So you have some RAM and disk, and you have some information about the cloud properties that you can use for your calculation. So here I'm connected to Google Compute Engine with Python 3 and with this impressive RAM and the impressive I don't know how to translate a disk, which is memory. Okay. And so it is possible to run my text. So what is also possible is also to introduce some data or some command and some additional file and to communicate between your notebook and this file with this command here on the left, which is file. Okay, here you have a command with this file symbol in which I can reach some files that are loaded on my drive, on my Google Drive, but I can also upload some files from data files directly to my drive within Colab. Okay, so I can import some file from, for instance, an Excel file with my data on my drive, and then go in Colab to go here. Here I have the possibility to go in my Colab, but in my Google Drive. If I don't make an error here, this is not my drive, but where is my drive? Here. But I don't make the link with my Google Drive here. But okay, let me go back here. Okay. If I remember well, is here. And here it is possible to upload some file from my own computer, my own drive. For instance, I can here upload a file of data, for instance, this Excel file, coin data. Okay. So here it is possible to upload a file, an Excel file, for instance, your data set, on which you will execute some computation, some calculus with a Python code in Colab and to get the result. It is also possible to export the result, and to export your notebook in different formats, in PDF, in a notebook, in Python code. To export the product of your computation, for instance, by creating an Excel file, which is located in your drive, Google Drive, etc., etc. Do you have some question about the general structure of Google Colab? No question? Do you see my screen? Yes?
Yeah, we can see it now. Yeah.
Okay, great. Okay, so let me start in a few minutes, but I will not have the time to. But I have prepared an exercise notebook in which we will discuss the decision tree, the cross-validation, and the random forest, etc., and the banking model. So I will send you the notebook Python to import it in your drive and to work with it. I will send you an email with all the way to proceed, but let me go here. So I have here on my drive this file that I will send you. So I will open with Google Colab. So I will explain you how to import and to get this exercise file with Google Colab. But so the most important point that we have to do is the fact that Google Colab is a collaborative platform. So if I send you with share here, I can share you my code. Okay. If I share you my Jupyter notebook, we will work together on the same file. So for some application, this is particularly useful if you want to write a paper, an academic paper, and you want to work together with a co-author, and we work on the code together. And so this is particularly useful. But for a lecture, this is maybe problematic because maybe you want to change something. And if you want to change something on your file, if I share it with you, then it will change my file. Okay? So that's why I will send you Jupyter Notebook. So you have to import it with Colab or directly to click and then Colab, it will be open with Colab, okay? But the first step that I asked you is to save a copy in your drive, okay? You have to save a copy on your drive. And then to work with this copy. Okay, so here, I don't know if you see on the top of my screen, but I will send you this exercise file. Then in file, save as a copy in Drive, you will create a copy of the notebook, Jupyter notebook that I will send you. And I ask you, please, to work with a copy of my file, because otherwise we will have some problem to collaborate together. Okay, so I work with a copy here. This is the first stage. I will explain all this stage in an email, and then I have to upload some data. So I will send you the data. So the data, we will work on credit scoring application. So the file is scoring data. Okay, and as you will see, the file is like this. So we have here a dictionary description of the variable. So we have a default variable that takes a value 1 or 0 if there is a default on the loan contract. And we have some informations about the credit owner. So the job tenure, the age, the car price, because it is a credit for to buy a car. Funding amount, the monthly payment, down payment, loan duration, credit event, married status, homeowner status, etc. And here you have the information for a set of 7,440 observations. Okay. So the first step for you will consist, one, to create a copy of the notebook Python that I will send to you. To open it with Colab, it's really easy because you just have to click on the link that I will share to you, and then you will open the notebook directly in Colab. Then you have to create a copy. And when you want to work with your copy, you can change the name, okay, rename, etc. This copy will be saved on your personal drive, okay? And then the second step will consist to import the data. So to import the data, okay, you have here to click on the file button on the sample on the left, and then to upload two files. The first file, so to upload a file, you have a sample here to upload your file in the workspace. Then you will choose a file which is a scoring data file, which is an Excel file in which I have the data. So I will upload this first file. Okay. So, okay, I have warning message, but you can see on the bottom of my screen, on the left button of my screen, that okay, the data are uploaded. And then I will also upload a second file, which is a Py file in which I have some codes to run. And this code is called function. Okay, I will explain it to you. So function, and then up, as you can see here, function.py is now uploaded. I have a problem with the scoring data, but in a few minutes, if you have a problem, redo the same. And send an email to Google to say that, okay, why it doesn't work, etc. But you can see in the second trial it works, and then I have my data set and the Py function in which I have some code to execute. Then here I have some block of text here. See, I will translate the text are in French, but okay, I consider that it is really understand. And then I have some blocks of Python command. And for instance, here in this block, I import some different packages that I have to import to run my code. Okay, so I will not explain to you why, but okay, for instance, you observe that we import some part of scikit-learn. So this is a package in which I have many functions to do machine learning model, machine learning evaluation, cross-validation, whatever, etc. And so, for instance, I will import from the scikit-learn tree package the decision tree classifier function, etc. Okay. I will import XGBoost, and I have renamed the XGBoost package as XGB to simplify the notation. Okay, because I will, for instance, ask to run a particular function in XGBoost, and I will say XGB point the name of the function, and then it will take the function in the package XGBoost and take the related function. Okay, so this type of environment, and then I can run this part, and there is no particular message except on the left. This part of the code run in 3 seconds, just to say there is no problem, there is no message, so there is no problem. Just import some packages. So just the main package that we will use is scikit-learn, and scikit-learn is a package to do machine learning in Python. Okay, and scikit-learn, I hope that you will understand everything in scikit-learn. Okay, you can do classification, regression, clustering, dimensionality reduction, model selection, pre-processing of the data, etc., etc. Okay, and you have very good documentation. Why scikit-learn is very popular? Because there is a very good documentation in scikit-learn, contrary to other toolbooks. Okay, and so for instance, you have a user guide. Okay, user guide, what I find in user guide of scikit-learn, supervised learning, you know what it is. Unsupervised learning, you know what it is. Model evaluation and selection, visualization of the model, data transformation, etc., computing with scikit-learn. For instance, if I consider the supervised learning, linear model, linear quadratic discriminant, kernel, super vector machine, this is the type of algorithm that I can use to make a supervised learning, and the algorithms that will interest it are the decision trees. And the decision trees, you observe that I take where I find my graphs, and you have classification and some example that explain you how it works, complexity, but you know that cart, etc., mathematical formula, you will find all we discussed before. Let me go back to my Python notebook. Then the second part is the fixation of the seed. So for many algorithms, there is a stochastic part. I don't have the time to detail, but some algorithm will have a stochastic component. Let us imagine that, for instance, we do a decision tree with a random split, you know? So the algorithm will choose randomly the variable for which it will compute the decrease in impurity. The problem with that is the fact that if I redo the same exercise, I will not get the same result. Other example, when I consider 2 samples, train and test, the first step consists in drawing individuals and affect them either in the training, either as a test. If I redo the same step of building, training, and test set, there is a new random draw, and the individuals who are in the test are not the same as before. And so I will not get exactly the same result. And when you do machine learning, the first step consists in considering, in fixing what we call the seed. And the seed is related, is a fact to control the randomness of your algorithm and to obtain exactly the same result when you redo a random sampling. Okay? And so in many times we will fix the seed. It means that I want to redo exactly the same random trial that I've done before. And I will get exactly the same result, a perfectly reproducible result. Then, okay, we will use the Panda package, and the short name for Panda is PD, to import my Excel data file. You just have to know that, okay? If you want some discussion about Panda, okay, Panda is not the animal, but Panda Python, okay? It's a package, a library that is just to manipulate the data. So to import data, to manipulate the data in Python, okay? And the simplest way to import an Excel file is to use in Panda library the function read Excel, and you just have to say, okay, I want to import this file, scoring data XLX, to indicate what is the cheat name. Remember that the structure of my file is the following. I have two cheats, and the cheat name of the cheat where is the data is data. And index column, just to say, it's just the index of the column for which you have in which you have the index of the observation. Okay, the name of the individual or what you want. Okay, in my example, the name of the individual in my or the index, what you want of my individual is reported in the first column. Be careful with Python. The number of the first column starts at 0 and not at 1. For instance, me in MATLAB, when I use MATLAB, the first column of a matrix is 1. The second is 2. With a Python, when I have a matrix, the first column is indexed by 0. The second by 1, the third by 2. Okay, so when I say index is equal to 0, it means that the first column of my file contains the index of the observation. Okay? And then the command, I save all the data in structure, okay, whatever the name of this structure, which is called, and the name of this structure is data. And then by using the here command data point id 10 means that I want to display the 10 first lines of my data structure. And then here, if I run my code, then I import my data and I report the 10 first line of my database. And then I have the default, the job, tenure, the age, the car price, the funding amount, the loan duration, the monthly payment, the down payment, the credit events, my status owner for the 10 first individuals. So for next week, I will ask you to reach this stage. And then we will go further to investigate, to run, to estimate, to train decision tree, to control for the overfitting, etc., etc. Okay. So I will send you an email with all the strategies that you have to follow to reach this step, just to import the data in a new notebook on Colab. Do you have some question? No question. So thank you and see you next week.